This is a problem that I solved for a student who lives in Italy and studies pharmaceutical chemistry. So it is not a faculty of mathematics or physics. But I think that it is an interesting problem, so I want to show you how it can be solved. It's actually also a high school problem in Italy, so it's not too complicated, but it is quite interesting and I want to show you how to solve it. So I have translated the problem and first we will read it and then we will solve it. It will not take too much. A square coil whose side is equal to capital L and its electrical resistance is equal to capital R is extracted from a constant and uniform magnetic field. The magnitude of the magnetic field is B, and the coil is extracted at a constant velocity v in a direction which is parallel to the plane of the coil. The magnetic field forms an angle alpha with the plane of the coil. If the coil cannot rotate, find the force which must be applied to the coil in order to extract it from the field. So this problem can be sketched, and let me sketch it here. Let's take a look at the coil from above. So here we have a square coil. We know that the side of the coil is equal to capital L, and this coil is immersed in a magnetic field. But now we want to extract it from the field. So it means that at some point t, here we have, for example, the area which encloses the field. So for example, here we can see the field coming out of the plane, and it's not perpendicular to the coil. So in this case, if I sketch it like this, it seems perpendicular. So I also have to make a side view. Here we have the coil seen from this side, for example, or this side, and the magnetic field is coming out of the coil like this, in a direction which forms an angle alpha with the plane of the coil. So this is the normal to the coil, and this angle here will be 90 degrees minus alpha, of course. And we are going to extract the coil with a certain velocity v. So it means that after some time, we are gradually exiting this area where the field is located, is present. So for example, at some point, the coil will be in this condition, where on the left, here, we will still have the field. So there is some kind of flux through the coil only in this portion of the area, whereas there is no flux here in this area, because this area is outside of the field. And this length here is simply equal to the velocity with which we extract the coil from the field, multiplied by the time that has elapsed starting from the initial position where the coil is completely immersed in the field. So it means that the area A of t of the coil depends on time, and we can write it as a function of time like this. It is equal to this length here multiplied by this length here. So I'm writing down not the area of the coil, because the area of the coil is simply L squared. But what I'm writing down, what I'm interested in, is to write down the area which is still in the field. So it is L times L minus Vt. So at time t equal to 0, A of 0 will be equal to L squared, which is the total area of the coil. But after some time, the area through which the magnetic field passes will be decreased. And why are we interested in the area? Well, because we need to calculate the derivative of the flux, phi of t. And the flux phi of t will be the magnetic field vector multiplied with the dot product by the normal to the surface, and then we multiply by the area A of t. And B dot n will be simply equal to the mode B times the mode of the unit normal, but that's just 1, and then I have the cosine of this angle here, but the cosine of that angle can be written as the sine of alpha, because it will be the cosine of pi halves minus alpha. And if I write down the derivative would be something like this: b sine alpha times the derivative with respect to time of a of t. But if we take a look at that expression, this derivative will give us minus LV. So this is equal to minus BLV sine alpha. And the electromotive force that I will call FEM, this is from the Italian forza elettromotrice, but so this is just notation. So this will be the electromotive force, which is a voltage, and it is the voltage that's created on the coil. And it will simply be equal to, let's take the absolute value of this, so it's just BLV sine alpha. So this is due to Faraday Neumann Lenz law, and it has to do also with Maxwell's equations, but it is a law of this kind. So usually you write it like this: the electromotive force is equal to minus the derivative with respect to time of the flux phi of t. And now that we have the voltage applied to the coil, this will be equal to the electrical resistance in the coil multiplied by the current that's present in the coil. So this current I is generated by the magnetic field, and in particular by the flux. So by the fact that we are extracting the coil and this area is changing with respect to time. Otherwise, if the flux did not change, then the derivative would be zero because the area would be constant. And from here we get that I, the current, is equal to BLV sine alpha divided by the resistance R. And from here we can calculate the energy per unit time that we lose, that I will call it PD. So it stands for dissipated power. So it's energy per unit time that we lose. And this is equal to the, thanks to the Joule effect, it's R times I squared. So the resistance multiplied by the square of the current. So it is B squared, L squared, V squared, sine squared alpha divided by R. And you can see that if we did not extract the coil from the field, this velocity would be zero, and therefore we would not dissipate any energy per unit time. So we need to do some work in order to be able to dissipate this kind of energy per unit time. So it means that if we really want to extract the coil, this kind of dissipated energy should be equal to the mechanical work per unit time that we do. So it means that this is equal to mechanical power, PM, and it is simply equal to the force F multiplied by the velocity V. So it means that we are applying a force in this direction, F, which is parallel to the velocity V. And this is how we can write down the formula for mechanical power. We know that the coil cannot rotate, so it means that this is the only power that we are inputting into our system. And therefore we find F. F will be equal to B squared L squared V sine squared alpha divided by R. So this is the final formula, and it is also the result for the problem.